In this lecture, I'm going to be talking about another approach for name entity recognition, and we consider this NER task as a dependency parsing task, because in dependency parsing is the relation between two words in a sentence, and we use the same kind of perspective for NER. So I'm going to be explaining this paper in 2020. NER is a fundamental task in natural language processing, concerned with identifying spans of text expressing references to entities. NER research is often focused on flat entities only, ignoring the fact that entity references can be nested. For example, Bank of China, this is a place, geopolitical, this is a place, country, but this is a bank. When it is in this context, then it becomes, so it's a nested NER instead of just flat NER. So in that paper, they use ideas from graph-based dependency parsing to provide a model, a global view on the input via a biaffine. And of course, Christopher Manning in 2017, I've explained this paper, has explained this biaffine model that they used for dependency parsing, and they used now here in this paper they used the same idea. The biaffine model scores pairs of start and end tokens. So we only focus on so we need two words in a sentence to see the relation, but our pairs are start and end tokens in a sentence. So it's not just any pair, it's start and end token, which we use to explore all spans so that the model is able to predict name entities accordingly, accurately. So this is the architecture of this model. That first we have a bi-LSTM, but you can use transformer architecture here because you just want a representation of your words in a sentence. Then you find the start token and the end token because you check different combinations and see which one matches so that you can score. So the model is inspired by dependency parsing, as I said, from Christopher Manning in Stanford in 2017. They use it for dependency parsing. And the figure that I showed you shows an overview of the architecture. And to encode the words, they use both BERT large and fast text embedding. For BERT, they followed the recipe of this 2019 article to obtain the context-dependent embeddings for a target token with 64 surrounding tokens each side. For a character-based word embeddings, they use CNN, convolutional neural networks, to encode the characters of the token. Because if you concatenate the word and the character, then you feed it to the bi-LSTM, it's just a better word representation. And after obtaining the word representation from the bi-LSTM, they apply two separate feed-forward neural networks to create different representations. So this is start and end, the representation for start and end of the spans, and using different representation for the start and end of the spans allows system to learn to identify start, end, or end of the span separately. This improves accuracy compared to the model which directly uses the outputs of the LSTM, since the context of the start and end of the entity are different. Finally, they employ a biaffine model over the sentence to create this tensor. This is scoring tensor. So finally, we just need this scoring tensor. And L here is the length of the sentence. C is the number of NER categories. And +1 because we have others, which are non-entities. So we can compute score for span I, because span I has end and start, different start and end. And then the tensor R sub m provides scores for all possible spans that could constitute a named entity under the constraint that your start should be less than end. Well, start of the entity is before its end. And they assign each span a NER category Y prime. So if we get the maximum of this RMI tensor, then that's the answer. Then we then rank all the spans that have a category other than non-entity by their category scores in descending order and applying following post-processing constraint. For nested NER, an entity is selected as long as it does not clash the boundaries of higher rank entities. We denote entity I to clash boundaries with another entity J. If this happens, then there is a clash. For example, in Bank of China, the bank of this entity clashes this one clashes boundary with entity Bank of China. So it clashes with this one. Hence, only the span with higher category score will be selected. For example, Bank of China will be selected because it has higher score. And for flat NER, we apply one more constraint in which any entity containing or is inside an entity rank before it will not be selected. And the learning objective of our name entity recognizer is to assign a correct category, including, of course, others, to each valid span. Hence, it is a multi-class classification problem, and we optimize our models with just softmax cross entropy. For parameters, as you see, for BiLSTM they use hidden size of 200. They just use 3 layers, and they have a relatively big dropout. I see. Feed-forward neural networks is a medium size, smaller feed-forward dropout in comparison to BiLSTM dropout, which was bigger. BERT size, okay, this is the default. And BERT layer, the last 4. They picked the last 4, and fast text embedding size, and then optimizer learning right is fine. And embedding dropout. So there are 3 different dropouts: embedding dropout, feed-forward neural network dropout, and this BiLSTM dropout. This one is higher. Then we have this dropout, and then we have this dropout. And then their model has an F1 accuracy of 89%. So they reformulate NER as a structured prediction task and adopted a state-of-the-art dependency parsing approach for nested and flat name entity recognition. So this system uses contextual embeddings as input to multi-layer BiLSTM. And they employ this bi-affine model of Christopher Manning to assign scores for all spans in a sentence.